So what we're going to be doing is thinking about how interactions between things affect the acceleration of objects. And then once we can determine an object's acceleration, then we can figure out how its motion will change over time by using kinematics. The other big piece with kinematics that we introduced was the idea of two-dimensional, and by extension, even though we didn't do any of this work, three-dimensional work where we look at motion along one-dimensional axis at a time. And then in order to determine how an object moves in two or three-dimensional space, we then combine those axes together using vector math. So all of that stuff is underlying everything else we do. And as a kind of warning, word to the wise, we're going to start moving more quickly. So some of you have felt like we're moving too quickly already, and I know that. Some of you have felt like we've been moving at just the right pace. You're going to find yourself mildly challenged, and some of you are have been itching to move a little bit more quickly. So we're gonna step things up, and that means that those of you who are still in a place where you don't quite get the whole vector stuff, or the kinematic equations are not easy for you to work with, if you still don't quite get the distinction conceptually between things like velocity and acceleration, you're going to need to do a little bit of work outside of class. That might mean looking at the recordings that I've made. That might mean coming and talking to me. It could also mean looking at a book, or going to Khan Academy, or talking to a friend or a relative who's pretty good at this stuff. But I will help you. I'm not saying I'm abandoning you, but the bulk of the legwork is going to have to be done by you. We're not going to do it in class. So what we're going to start off with today are kind of the basic rules of forces. And the basic rules of forces, we call them Newton's laws, and we'll talk more about this because it's interesting, but the truth is Newton's laws are not really accurate. We know that now. We figured out with relativity and quantum mechanics that they just don't work. But for things that are relatively small, relatively not too small, not moving too quickly, things that don't have extreme masses, they work just fine, and that's what we're going to stick with. So you won't have to deal with the fact that all objects actually exist as probabilistic waveforms, because that gets a little confusing. And what Newton's laws are going to allow us to do, what we're really going to focus on, is when you think about any single object, we want to be able to apply Newton's three laws to it to either determine how it might move in the future, or to be able to look at how it's moving and determine what kinds of forces must be acting upon it. Okay, and those are the two big things that we're looking at. We're going to look at it from both sides. Side one is we're going to say, okay, well, if we know enough about forces, then we can predict how an object is going to move. The flip side of that is, if we observe an object's motion, from that we can infer a bunch about the forces that are acting upon it. Both of those things are equally important. And so it starts with this idea of what is a force. And when we think about forces, it's actually kind of crazy because we don't really know what they are. Like when you look at particle physics, they have all sorts of theories about how these forces are communicated between objects. But from a classical mechanics standpoint, from Newton's laws, we don't really know exactly what's going on. We just know that they happen. And forces are just pushes or pulls. And we measure them either in newtons, which is what we're going to do in this class, or pounds. And pounds seems weird because how is that a unit of force? That's a unit of weight. Well, weight is a force. Weight is the magnitude of the force from a gravitational field on an object. So if my weight is 145 pounds, what that tells me is that the Earth's gravitational field is pulling down on me with a force of 145 pounds. That's what that number means. And if I were somewhere else, like on the moon, my weight would literally change. the moon would be pulling down on me with a force of about 1/6 that, so like 22 pounds, my weight would change. And we're not going to use pounds too much. And in the metric system, when we talk about people and like animals and things like that, we don't use the force of the Earth's gravitational field. Instead, we talk about mass. So in the metric system, typically we'll describe like an adult human's mass in kilograms. And the weight of that person is the size of the force that the Earth is, with which the Earth is pulling on the person. So my mass might be 70 kilograms. My weight would be 700 newtons in the metric system. But they're just pushes and pulls. And we know, I think you all can understand this idea that objects can experience more than one push or pull at the same time. All of us are experiencing at least two forces right now. One, a downward force from the Earth's gravitational field. The other is the upward force from whatever is preventing us from falling straight down, right? In my case, it's just the ground. In your case, it's some combination of the ground and the seat and the table. All of those things are helping to support you. The only time you're only experiencing really one force is when you're mid-jump. When both of your feet are off the ground, then you're, for the most part, only experiencing one force, which is the downward force from gravity. And we're going to go into 3.9 minutes more down the road, but the way that we're going to depict forces is by using these drawings, and the drawings are going to show an object as either a dot, or I will almost always use a rectangle instead, just because you'll see why down the road, and then we'll use arrows to indicate the size and direction of the forces acting on that object. Those arrows represent vectors. They don't show us motion. Those arrows are showing us the size and the direction of forces.
I just want to see if it's about freezing.
Oh, it's not. I mean, it is, but just barely. Yeah.
It was -1 Celsius this morning.
Yeah, it was colder than that at my house. It was like 24. And then when we think about, okay, well, what is this connection between forces and the way an object moves, we have to think about how all of the forces together work. And so essentially what we're going to be doing is mathematically combining forces. Forces are vector quantities. They have a magnitude and a direction, which means what we're going to be doing is thinking about the vector sum of all the forces acting on an object. And that is going to be kind of our critical quantity. Each individual force matters, but what determines whether an object's motion changes or not is its overall force. So Newton's laws are kind of the basics for thinking about how forces govern the motion of objects. And what we're going to do is we're going to watch 3 videos that are really kind of fun, but also there are some fundamental inaccuracies in the vocabulary. So what I want you to see here, and you'll enjoy this because it's neat, but the words that they use are less important than what you're seeing. So just pay attention to what you're seeing, and as they talk, recognize that they're not speaking very precisely. They're really good at what they do, but they're not physics teachers, and so some of the stuff that you're going to see is just not quite correct. And I will fix all of that stuff in the mix, as they say. Okay, so we're gonna watch this person doing what? Cutting grass with scissors.
That's so
Crying
stupid.
out loud. All right, and now we're gonna actually watch the video. Okay, so what's neat about these videos is that they are in space, and in space there's no apparent gravity. There is gravity actually, but it's not. It doesn't affect the motion of objects the way that we think it does. So, for all intents and purposes, we can pretend that there is no gravity acting on any of the objects in this.
Stay at rest, and things in motion stay in motion.
Okay.
First law says, things at rest, and things in motion stay in motion, unless those things have a force imposed on them. I have a bag of candy-coated chocolates, one of our favorite things up here. So let me take one or two of these out. Uh-oh. Wait for me. Move it out here. Okay. All right. Let's pretend like I'm on the ground in your classroom. And if I were to take one of these candy-coated chocolates and let go of it, what would happen? Well, it would go crashing onto the ground, wouldn't it? And then when I ate it, it would have to be a dirty chocolate that fell on the ground. The reason that happens to you in the classroom or on the ground is there's a force exerted on the chocolate, and that force is provided by gravity. Okay? And that force is always straight down. So if you were to drop the candy-coated chocolate, it would fall to the ground because it has a force imposed on it. But here in the space station and in low Earth orbit, we are under microgravity, which is essentially no gravity, no apparent gravity. So if I let go of the candy, it doesn't fall. It stays at rest because there's no external force on it. Okay? Actually, there's a little force because we have fans going, and so the force is provided by the airflow. But basically, there's no force on it until an external force is imposed on it. Like that. Matter has no motion unless you impose an external force. And actually, my finger is an external force here.
So I'm going to pause it there for a second and say, so two things. One is, this I think is one of those things where as you watch it, it all seems obvious, but he just said something. He said, matter has no motion unless an external force is imposed upon it. That's not right at all. Just so you know. And the kinds of things that I want you all to be doing, and I know it is freezing in here, I get that, it's cold, and we just had a break, and some of you, like me, didn't sleep at all last night. So a whole bunch of reasons why we might not be locked in. But I want you to at least like make your best effort to really think about what you're seeing here. Because when you saw that that M&M, like watch it for just a second, okay? Watch what he does, okay?
So it stays at rest.
Do you see it moving? He just said it stays at rest, but it's moving.
Until
He can't even stop it. Look, no matter what he does, he can't stop it from moving. At the same time that he's saying, matter will have no motion unless it's acted upon by a force. At the same time that he's saying that, that thing is moving constantly.
Yeah, when
What's
trying to-
going on?
Well, when trying to stop it, then that would create force, right? A little bit of it.
Yeah, but then now he's not touching it. I mean, if I move through this, you can see, look, it's moving, right? It's not staying still. Nothing is touching it. There's no gravity. What's going on,
You
Max?
said it's because there's fans going.
It's not because of the fans. That's a great point. He said the fans are moving, and there is some motion of air in there, but it's not the fans. That's not what's going on. Khalil?
Well, if he doesn't stop it perfectly, then it's still in motion.
But he said matter will remain motionless unless there's an overall force acting on it. Are you disagreeing with him?
Yes.
Yeah. What's your hypothesis
Well, I
here?
would say that it's true, but it's not quite, you didn't word it quite correctly, because if it's in motion, then it will stay in motion. So once it's been acted on, then it
Yeah. So there's two parts to Newton's first law, and he told us one of those, which is if there's something that is motionless, it won't start moving unless there's an overall force. The part that he left out is if something is already moving, it will keep moving in the same direction, at the same speed, until it's acted upon by a force. Those are the things I want you to be thinking about that. Like, there are mistakes that are being made in here. He's a great guy and he knows what he's doing when it comes to like running a spaceship, but he's not an expert on Newton's laws. They just put him up to this because he's in space right now, which is pretty great.
Okay. What you're saying, that's just a tiny little piece of chocolate. That's easy, right? What if that little piece of chocolate had peanuts in it? Would that change it? Well, let's see. That's a good question to ask, and that's why we run experiments. Answer good questions. So here we have a candy-coated chocolate with a peanut inside. Now, a peanut's pretty heavy, so that's going to make it fall, isn't it? Okay, let's see. No,
It's
things
moving.
at rest. Stay at rest.
See it moving.
Okay, no matter how big they are, no matter if they have peanuts in them, or almonds, or little crunchy bits. Okay.
I feel like it was moving less than normal without a peanut.
So my wife got me this weird new toy.
This is not part of it. So think about what you just saw, and think about how what you just saw was, there was some accuracy there, but there were some parts that were obviously not accurate. I mean, he kept saying over and over, things will be motionless unless there's a force acting upon them. And Khalil pointed out that that's only half of the story. Okay, so now let's watch another ad, probably. So let's watch another one, and this one has to do with Newton's second law. So that was Newton's first law, and we'll go into it in more detail, but now we've got Newton's second law to think about.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force in our bungee cord here. We'll put it on our bungee, and we'll pull it back. And you can see how fast it accelerates because there's very little mass. Next we'll try a little spaceship. A little more massive, and you can feel it because as you move it, you can feel the kind of force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot.
That's not the fan, is it?
Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Go back the same amount on the force, and here we go.
Okay, same deal. That's not fan that's pushing that around.
There you have it.
Unless there's another force that acts on it, it's going to keep moving.
Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again.
Okay, and the last of Newton's laws is Newton's third law, and this is the one that is, I think, most misunderstood. My guess is that very few of you could apply Newton's third law with 100% accuracy, and it's not your fault. It's not your fault. It's because you have been taught a version of Newton's third law that doesn't quite make sense anymore. So does anybody remember what Newton's third law is? Newton's third law is the one that's really easy to say. Jesus?
For every action, there's an equal and opposite reaction.
Yeah, for every action, there's an equal and opposite reaction. So when you're in your car, how many of you drove to school today? Okay, when you're in your car, Jonah, and you push on the gas pedal, that's the action. What's the reaction? the car goes forward, right? Jim, you don't think so? Yeah. So what's interesting about the way that Newton's third law is typically framed is that it sounds like one thing happens and that causes another thing to happen. So when you're driving your car, you push on the gas pedal. That causes gasoline to go through the fuel injectors into the engine. That increases the rate of the expansion of the cylinders. That makes your engine go faster. That makes the axle turn faster. That makes your car go faster. So for every action, there's an equal and opposite reaction. But those words aren't quite right. When we talk about Newton's third law, we're not really talking about an action followed by a reaction. So what Jim said is, when you push on that gas pedal, it pushes back on you. That's what Newton's third law says. And it isn't that you push on the gas pedal and then the gas pedal pushes back on you. It happens at the same time. There's no time lag for Newton's third law. So we'll talk a little bit more about this in a second, but to start with, let's watch, and again, you're gonna hear this astronaut say over and over, for every action there's an equal and opposite reaction. So just be aware that's not quite right, okay? Add.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrust is expelled one way and vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground. At least not while getting this much hang time. All right, back to serious business. Got a basketball right here. Going to be object 1 on the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied the force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth.
All right, and that, of course, is what we're going to be doing. So let's talk a little bit more about each of these, because what I want to do is clarify how we're going to be using these three laws. So the first law, what the first law says is that acceleration is caused by overall forces. So remember I mentioned that objects can experience more than one force. And if you take all those forces and add them together using vector math, you'll get one number in one direction. That number represents the size of the overall force. The direction represents the direction of the overall force. That will determine whether or not the object accelerates. If there's an overall force, it'll accelerate. If there's not an overall force, it won't. So how do we use that? Well, we can think about magnitude and direction of forces, and we put that together with the fact that acceleration has a magnitude and direction as well. And what we're gonna look for is, do we see acceleration? If we do, then there's gotta be an overall force. If we don't, then there is no overall force. If there is an overall force and we know it, then we can predict how the motion of an object will change. So let's look at kind of the classic example here, and I'll tell you what I'm gonna do. I'm gonna do this twice. I'm gonna put the coin on top of a note card, sitting on top of a cup. And first, what I'm gonna do is I'm gonna pull this slowly toward me, all right? And right now, everything is at rest. So that means there's no change in motion. With no change in motion, there must be no overall force. But if I pull slowly on this card, then the coin starts to move toward me. That was a change in motion. That change in motion is acceleration. It's accelerating toward me. What does that tell us? There must have been an overall force in my direction. Okay? What happens if I pull it really quickly? What happens if I pull it really quickly? Well, if I pull it really quickly, I can't do it because I'm too shaky, then it falls down and goes into the cup. So if it falls down and goes into the cup, that must mean that the overall force was down. So I was pulling one way, the overall force on the coin was a different direction. So we can determine what forces are acting on an object by observing its motion, whether that motion is changing. We can also, if we know what forces are acting on an object, make a prediction about what's going to happen, right? So we can work both ways with Newton's first law. Newton's second law is mathematical. Newton's second law relates the size of an overall force on an object to the size of its acceleration and the size of its mass. And the direction of acceleration and the direction of force are going to be the same as well. And basically what Newton's second law says is that if we take an object and we apply a larger force to it overall, then we should see a greater acceleration. So if I have this chair and I create an overall force, now I am not the only force acting on this chair, but I have the ability to generate a force overall that is in this direction, and it starts to accelerate, and we can see its speed changes once I apply a force, and the other forces acting on it don't counterbalance that force. If I apply a larger force, we see larger acceleration. So I was able to engineer a situation in which the overall force on that chair was smaller and then larger, and the smaller force resulted in less acceleration, the larger force resulted in more acceleration. Okay, Cole, can you come up here for a second? Now, I'm gonna add mass to this chair, hop aboard, and now if I push with that same larger force, thank you, you can go back to watching YouTube. With that larger mass, it resulted in less acceleration. So acceleration is proportional to the overall force and inversely proportional to the mass. And it's the overall force that matters. So the size of my force is not necessarily relevant. It's the size of the overall force that matters. So for example, if I choose an object that is a little bit more difficult to move, I can pull on it with a small force, or I can pull on it with a pretty large force, and there's no change in motion either way. What does that tell me? It tells me the overall force didn't change. I was able to pull on it with a small force and with a large force. Right now, I'm not pulling on it with any force at all. 3 different forces, same change in motion, no change in motion at all. So that means no matter what I did there, doing nothing, pulling with a small force, pulling with a larger force, I was not able to engineer a situation in which the overall force changed at all. So when we think about Newton's second law and we think about forces on an object, we tend to think about the forces we are applying. We are the force makers in our own universe, right? If you're pulling a wagon, you're providing the overall force. If you're driving a car, you're providing the force. Anything we move around, we think of us as providing the force. That's not exactly right, though. We are providing a force. Our force, in combination with all the other forces acting on the object, determines the overall force, and that's what really matters. Sometimes our force is so much larger than every other force acting on the object that effectively it's as if we're the only force acting on it, even if that's just for a small amount of time. If I throw a baseball across the room, what determines the motion of the baseball the moment that it leaves my hand is basically the force of my hand on the ball. That's basically, like, all the other forces acting on it are so small that the only one that really matters is the force of my hand on the baseball. But if I go outside and I try to push a car around, it's really different because there's all sorts of friction going on with the car. And the Earth's gravitational pull on the car is pretty large. So if there's a little tilt on the parking lot, that's adding a force as well. So if I were to go outside and there were a car that were on a slanted surface and I were to start pushing it and that car started rolling down the slanted surface, it's not really me. I didn't really do that. It's just rolling downhill. So sometimes our force matters more than others. But our force is, in general, never going to be the only force acting on an object. Okay, the last of Newton's laws is Newton's third law, and this is the one that's tricky because what we tend to think of is okay, well, if I walk over and I bite Cole's ankle, then he's gonna kick. And so there was an action, me biting his ankle, and there was a reaction, him kicking. Or if I walk up to Ben and I tell him, hey, Ben, you look great today. And his response is going to be, you look crappy as always. So there was an action, my compliment, and a reaction, which is the closest thing that he's got for me in terms of compliments. But those things are not Newton's third law. Newton's third law doesn't describe one thing happening and then another thing following. Newton's third law is real specific. It tells us that anytime there is a force, there will immediately, instantly, at the exact same time, be another force. That other force will occur concurrently with the first force. That other force will be in the opposite direction from the first force. And that other force will have the exact same magnitude. So the way I think about Newton's third law is you kind of think basically describe a force between two objects and then switch the objects. So if I push on the wall pushes on me. If the lever pushes on the cord, then the cord pushes on the lever. If a duck pushes on a piece of algae, the piece of algae pushes on the duck. And the motion of each object might change because there might be an overall force acting on the object. And that can be really different depending on the masses of the objects. If I push on this piece of paper, it pushes back on me. When I do that, the paper accelerates in the direction of the overall force acting on it. I am not accelerating in the direction of the force acting on me. And the reason is because I have a much larger mass and my feet are on the ground. So there's a bunch of other forces acting on me and I'm massive. So the behavior of the two objects can be really different. And the way I like to demonstrate Newton's third law is with your finger, and you can do this, just be sort of cautious about it. You can do it with the tip of a pencil works best, or the tip of a pen, or you can use the back if you have like Ella's got a felt tip, so we don't want to do that. But basically, if I look at my finger right now, it's just a regular old-fashioned finger, and then if I push on the tip of this pencil, and I'm not pushing very hard for just a second, so I'm pushing on the pencil. Now I look at my finger and there's a dent in it, right? And if you do that, you'll see a dent in your finger too. there's only one way you can get a dent in your finger. That's if something was pushing on it. I pushed on the pencil, it pushed back on me. So for Newton's third law, state what's going on in terms of forces and reverse the objects. The mop pushes on the floor pushes on the mop. My sock pushes on my shoe, the shoe pushes on my sock. Always the exact same size, opposite direction. The forces are occurring at the same time. And then the last thing that I just want to bring up, because you're going to need this when we're working through the simulation, is friction. Friction is a force. And friction is a weird force because it can change. And the way that it changes depends on all the other forces acting on an object. And basically what happens is that friction is kind of a slowing down force. Essentially, if you have an object that is moving along a surface, friction will be slowing it down. Friction will be in the opposite direction of the object's motion. If the object isn't moving, then friction is acting on it if it would be moving if there were no friction, which seems like a weird thing to say, but like, look at this cup on the ramp right now. Is there friction acting on the cup? Well, what would happen if there were no friction? That's not gonna work because too much friction acting on that card. If I put something on the ramp that doesn't have much friction, it starts to move down the ramp. So what's keeping the mug here? Friction. Sometimes we can tell, and sometimes we can't really easily. If I put the mug on this table, I don't know, it's not going anywhere. Is there friction acting on it? It's hard to tell. If I take something that really would requires a level surface, I can find out. When I put this ball bearing here, it starts to roll off the table. So now I know friction must be acting on this mug. If I put the ball over here though, it stays still. So if I put the mug over here, probably there's not that much friction acting on it. A little bit. If we were to turn off friction in this room, many of the objects resting on these tables would start to accelerate. And they would slide along the surface in whatever direction it's slanted. If we can see the slant, we can guess what direction the acceleration will be. But if we can't see the slant, then a lot of things in here look really level, but they're not. There's nothing in here that's perfectly level. Okay, I want to show you one last thing, which I feel like is worth thinking about. So if we take, so this is the simulation, and I'm going to have you all play around with this. Those of you who were in the regular physics class, you had time to do this on Tuesday of last week. Those of you in AAP, you didn't look at this because we were going over the test that you took. But here's what I want you to think about. Okay, so first of all, there's a bunch of questions on the assignment, forces and motion simulation activity. And you can work through all those questions, and you should. But I also want you to be thinking about Newton's 3 laws. What's going on in this picture right here? Well, Newton's first law says that objects that are at rest will stay at rest unless there's an overall force acting upon them. Objects that are in motion will continue to move in the same direction, the same speed, unless there's an overall force acting upon them. Now, what can we tell about what's going on here? Not much, really. I mean, it looks like there's a net force to the left. There's an overall force to the left here, but I don't see any motion, and I think that's because it's paused. Okay, so it's paused right now. So, is it at rest? Is it moving? I mean, we don't really know. Newton's second law says that acceleration is a combination of the effect of forces and mass on an object. Overall larger forces will result in overall larger accelerations. Overall larger masses will result in overall smaller accelerations. And so when I look at this looks like it's pretty massive. I don't know. I mean, what do we know? Maybe we can figure it out. Let's see. Yeah, it's 50 kilograms. So that's 500 newtons. That's like, a small person. So be a lot, but I mean, this is a pushable thing. And the magnitude of the force, it looks like it's like 300 newtons being applied by this person, so I don't know, like, I don't know how much that is, but if we think about a person being about 6, 7, 8, 900 newtons, then this is like about the force that it would take, like about a third of the force that it would take to lift up a person. So, you know, we can do that. Like most of us could lift up another person. So this seems like this would be a pretty large force, but we could all apply that much force to something. And so we should see some acceleration here. When I hit go, we should see it accelerate to the left, right? And then Newton's third law says that if there's a force being applied from this person to the box, there's an equal and opposite force at the exact same time being applied from the box to the person. That's Newton's 3 laws. So what's going to happen when I hit play here? What do you think is going to happen? Any guesses about what we'll see? Box is going to start going to the left, right? Yeah. So let's see what happens. Uh-oh. It didn't go to the left. It's going to the right. Oh, wait, now it's going to the left. What happened? Why didn't Newton's laws correctly predict the motion of that object? What do you think, Tim? Was there still force being applied in the other direction? Great question. No, there wasn't.
I mean, the force still stayed for some time.
The force did not stay. There was only one force acting on this object, and it was to the left. It is not going uphill. Great guess, but it's not. TJ?
Was it moving?
Okay, so that is correct. It was already moving. And here's where, this is where it gets really interesting, because Newton's laws are easy, and you guys all understand this stuff. Unfortunately, you've done this stuff before, except that as soon as you were presented with a scenario that was designed to limit the amount of information you had, not only could you not correctly make a prediction, but you couldn't explain it. You had a couple of tries. One was, there's still a force acting on it. Why did he say that? Why did he say there's still a force acting on it? That's not what you meant, is it? What did you mean? It was moving, but he didn't say it's moving. He said there's still a force acting on it. And the reason he said that is because we all walked into this classroom, including me, with the misconception that for things to move, there must be a force acting on it. Because that's our experience. If I push this chair, it moves. And if I stop, it stops moving. Just like the astronaut said, things that are in motion, things that are motionless stay motionless unless there's a force. So we gotta push things to make them move. But that's not right. And then when we see something moving, we're like, well, there's a force acting on it. What's the force? It's the force of its motion. I hear that a lot, the force of its motion. Motion isn't a force. Motion isn't a push or pull. Motion is motion. What was causing this thing to move to the right when I hit play was that it was moving to the right before I hit play. Okay? When you apply force to a moving object, you change the motion of that object. It doesn't move in the direction of your force necessarily. This situation was the equivalent of a car rolling toward me very slowly. And if that car rolls toward me, and I put my hands out and I start pushing, it doesn't immediately reverse